Sphere and shell. We have a solid conducting sphere carrying a net charge q that has a radius a. That's this guy right here. The sphere is placed inside a conducting shell of inner radius b and outer radius c. That's this shape. Hang on, draw the inner part, and here's the outer part. So we have a sphere and we have a shell, and I'm coloring in where the material is. And now I'll erase that. The shell has no net charge. So this guy out here, there's no net charge here, and you have plus q on the sphere. Derive an expression for the electric field in terms of the distance r from the center of the sphere for the following regions. R less than a, that's inside the sphere. A less than r less than b, that's in the space between the sphere and the shell. B less than r less than c, that's inside the shell. And finally, r greater than c, that's out here. Then sketch the electric field as a function of r. 3 more parts to the problem. What is the charge on the inner surface of the shell? So we're looking for the charge here. Then what is the charge on the outer surface of the shell? That's there. And finally, sketch the electric field lines outside a spherical volume of radius r greater than c. So that's out here somewhere, greater than c. Here's our first region for finding the electric field, r less than a. You sketch your Gaussian surface with a radius less than a, and you find that since the sphere is a conductor, all of its charge must be on the surface. So that's out here. Therefore, the Gaussian surface encloses no charge. Using Gauss's law, the integral of E dot dA equals Q enclosed. Well, there is no Q enclosed. It's 0. So the electric field is 0. Now we want to find the electric field between the sphere and the shell. Once again, draw a Gaussian surface. Apply Gauss's law. The enclosed charge now is capital Q. We do the integral. E is constant. We take it outside the integral sign, and of course E dot dA turns out to be just EdA because they are in the same direction, so the dot product reduces the magnitudes of those two guys. You do a surface integral over dA, a closed surface integral. You get 4 pi r squared, the surface area of the sphere. Do a little division, and here's our electric field between the sphere and the shell. Find the electric field within the shell. Well, we know that the electric field within a conductor is 0, right? We determined that when we talked about electrostatic equilibrium. That means it encloses 0 charge in accordance with Gauss's law. So the answer is 0. Okay, so E is equal to 0 by the conditions of electrostatic equilibrium. But there's that plus charge Q on the inside. How can Gauss's law still work? Think about that before you go to the next slide, please. What's going to happen is the plus Q charge on the sphere will attract an equal and opposite charge, negative Q, to the inside surface of the shell. Since the shell initially was neutral, that means, because you have to have conservation of charge, that there will be a plus Q on the outside of the shell. So you add these two together and you get 0. So charge is conserved. But now when you do Gauss's law, you can see that the enclosed charge is 0, so the electric field is 0 within the shell. And finally, determine the electric field outside of the sphere and shell combination. So we have Gauss's law here. We say the enclosed charge is plus Q. We do the standard integration here, and the more times you do it, the quicker it'll come to you. And we find that the electric field outside is Q over 4 pi epsilon 0 r squared. So even though the shell was polarized in the last step, or we explained it in the last step, and we found that there was a negative Q on the inner part of the shell, a plus Q on the outer, when you add all these charges together, right, into Q on the sphere, Q minus Q plus Q, you still get plus Q, which is nice. So the enclosed charge is plus Q, and this is valid. Sketch the electric field as a function of r. First, label the axes, okay, and make sure you put the units in. So we have the electric field, newtons per coulomb, and the radius or the distance in meters. Draw lines for where the electric field is 0. And of course, what's handy is to have all 4 of them up here to make it look right. So from 0 to A, it's 0. Okay. And from B to C, it's 0. Then sketch a continuous. Okay, this is a step process, so don't worry yet. For all points where R is greater than A. This ensures that you'll have the correct E values for R greater than C. As you can see, the curve continues, right? It continues from A is less than R less than B. So just draw the entire 1 over R squared. You want to make sure you do that so you have this point in the proper position. It's going to be less than the value here, and it'll be less by a factor of 1 over R squared. Then erase this section. See where we have the dashed lines? Go ahead and erase that because you know the electric field between B and C is 0. Once again, this is the handiness of using a pencil during the exam. Next, add vertical lines to make the graph look continuous. Again, I'm not talking about mathematical continuity here, just so it kind of makes sense to you. Physically, it's impossible for the electric field to change instantaneously or to have 2 values at the same R position. So put the lines in dashed lines here. Okay, so that's here, here, and here. It's not required, but it is helpful. And again, although the word sketch, according to College Board, doesn't require the electric field values, some AP questions could ask you to label important values, so we went ahead and put them over there. Okay. We also labeled where A, B, and C is. What is the charge on the inner surface of the shell? We've actually already done this, but let's do it again. We draw a Gaussian surface in the conducting shell here, and there is no electric field within a conductor. That's one of the conditions of electrostatic equilibrium. So Gauss's law states that it cannot have an enclosed charge. But there is a plus Q here on the sphere, so what does it do? It polarizes the shell, and it brings in a negative Q for the inner surface so that the enclosed charge by that Gaussian surface is 0. So the charge on the inner surface of the shell, negative Q. What is the charge on the outer surface of the shell? We now have a negative Q on the inner surface. But the original charge of the shell was 0. Because of conservation of charge, you have to remain at 0. So how do you do that? The negative charge here is balanced by a positive charge on the outside. The negative charges that moved in here to the inner surface left behind positive of equal magnitude. So the answer is plus Q on the outer, minus Q on the inner. Now sketch the electric field lines outside a spherical volume of radius R greater than C. Where are they asking for? Right there, that's the radius of C. So we know that we have a positive electric field, so it has to point outward. And basically that's it. So draw the perpendicular lines equal in length, perpendicular to the surface, that's one of the conditions of electrostatic equilibrium, and pointing away from the shell.